So we start with the solution of the tutorial number 3, RL circuit and RC circuit. The first question, we need to find the voltage, the current through a capacitor. So we know that the formula for computing the current through a capacitor is that I equal C dV over dt. So I equal C over dt. So based on this, C dV, the current will depend on the rate of change of the voltage. So if the voltage is minus 20 means that the voltage is constant, so it doesn't change with time. So the current I equal 0, because this will become 0. In the second case, P, we have the voltage formula given by this. So we know that I equal C dV over dt. So we say C is equal 510 to the power minus 3, 2 times the derivative of the exponential terms will be just the derivative of the exponent, which is minus 5, times the exponent itself. So this will equal minus 50 e minus 5 t milliamp. The second one is also straightforward, so I will just give the final answer for this one. So remember the rule that you will be dealing with the capacitor in series as they are resistor in parallel. So the total capacitor, you will get the total capacitor. C will equal 3.62 farad. Okay, so the answer should be 3.6 farad. So this is 2 in series and all this 3 in series. So remember that when you take the 2 series capacitor, you deal them with them like parallel resistors. Number 3 is also straightforward. So number 3, sorry, this is the previous answer is for number 3. So previous answer. So this is equal C equivalent will equal 3.62 farad. This is the answer for this one. For number 2, sorry for this mistake. So for number 2, this one, number 2. This is number 2. So this is the answer. The answer for this one should be C equivalent. C equivalent should be 3.316 farad. Okay, so always check the calculation and the result of the calculation. For number 4, also it's a straightforward question. So we need to find the equivalent inductance for a combination of inductors. So here we have this. Remember this one you will not use it in the combination because you only use the inductor that are connected between the 2 terminals, but this one will not be considered in the simplification or the combination. So here I will write just the final answer. It will be 6.6387 Henry. Okay, now we go to question number 5. In question number 5, we need to find the voltage at t equal 200 millisecond. The voltage at t equal 200 millisecond. Now remember the rule. For this we need to find all the time. We need to find the 0 minus and 0 plus values, or the values of the current and the voltage before opening the switch and after opening the switch. So here we can see that we have inductor, so we will focus on the current. So IL0 minus, so the switch was closed for a very long time, so this inductor is short circuit, so the current here will be just 24 divided by 10, so it will equal 2.4 amp. And remember the rule that IL0 plus will equal IL0 minus, because the current through the inductor will not change in zero time. Okay. Now we pay our attention to find V0 minus. V0 minus, when the switch is closed, of course, V0 minus will equal 24. V0 minus will equal 24 volt. Now what happened when we open the switch? When we open the switch, the inductor current will not change in zero time. So here the current will be circulating in this direction. So here, but we can see that it's from negative to positive. So V0 plus will equal IL0 plus, but with a minus sign times 40. So minus IL0 plus times 40, so it becomes minus 96 volts. Now we want to find the time constant of the circuit. So the time constant of the circuit, what we will have only two resistors connected with the inductor. So T will equal L over R. L over R. L we have only 5 Henry, but R we have 40 plus 10, so they become 50. So here then tau becomes 0.1 second. Now we can write our final expression for V of t. So V of t will equal minus 96. Remember that we use the V0 plus value, not the 0 minus. Minus 10t, where we have our time constant is 0.1. So this will be valid for t greater than 0. Now at t equal 200 millisecond or 0.2 second, we have V.2 will equal minus 1.99 volt. Just a straightforward substitution. We go to question number 6. In question number 6, it's the same circuit, but now a similar circuit, not too different from the previous one. But here we need to find the voltage. We need to find the voltage for all positive values of the time. The same philosophy that we solved the previous problem. So here we have the current I. So the current IL will not change in 0 time. So we will use this fact. So IL 0 minus, when the switch was closed, so 10 over 4, because this was short circuit, so 10 over 4, so it will equal 2.5 amp. And we know the fact that IL 0 plus will equal IL 0 minus, which equal 2.5 amp. Now we only interested into the V for positive T, so we will not go to find V0 minus. V0 plus will equal what? Here, what you can see, the current is still circulating, but we cannot find the voltage from the formula, because we know that the voltage across the inductor is equal di over dt. We still not having the formula for I, but here from the circuit, the current that is going in this direction is IL. So I can write KVL. KVL says that minus V, here the voltage minus V, plus minus V, so minus here, this is the voltage minus V, will equal, the voltage here minus V will equal the current multiply by the resistor. The current multiply by the resistor. Or we can say that VL will equal minus VL 0 plus, of course, it will equal minus 4 plus 6, the resistor combination, times IL0 plus, times IL0 plus, which is mean minus 10 times 2.5, so it becomes, well, good. Tau, now we pay our attention to find the tau, so tau equal L over R. L is 5 and R is 10. So the inductance becomes, the time constant becomes 5 over 10. Okay, so this is our time constant. Then now we can write V L of t will equal minus 5e times t over tau, e minus t over tau. So t 10 over 5, which is equal minus 2t, minus 2t. Okay, so always check, as I told you, need always to check the you need to always check the values of this, the values of the parameter. So this will be voltage for t greater than 0. Okay, we go to question number 7. In question number 7, the circuit, in this circuit, it says that this switch has been closed for a very, very long time. So we need to find IL of t just before the switch opens, after the switch opens, and at different times, which is 15.8 micro, 31.5 microsecond, and 78.8 microsecond. So it's clear in this question that we need to find IL0 minus and IL0 plus, plus that we need to find the expression for t, which is valid for all the positive values of the time. So here again, we say that the inductor was a short circuit before the switch opens. Yeah, before the switch opens. So from this we can find IL0 minus. So IL0 minus will be the current through this inductor. So what you can see, when this was short circuit, of course, the current will not go through this 220 ohm resistor. And also it will not go through the 300 ohm resistor, because all of them, these two are in parallel, and they are in parallel with a short circuit. So all the 4 milliamp will go through the inductor. So it will equal 4 milliamp. And of course, again, IL0 plus will equal IL0 minus will equal 4 milliamp. Now we find our tau. So when this switch is open, we have only this circuit. We will have only this circuit. So tau equal L over R. So 210 times 3 over 200. So the time constant is 9.1 microsecond. So the final expression for IL of t will equal IL0 plus, which is 4 exponential times t over our tau, 9.1, 10 times minus 3, of course, in milliamp, which is valid for t greater than 0. Or for simplicity, I can say that 1, 0, 0, t. 0, 0, t. Okay. Now at IL 15.8 microsecond, you will find that it's equal this will equal 0.7, it will equal 0.703 milliamp. IL at 31.5 microsecond will equal 0.125. Please always check these numbers. IL 78.8 microsecond will equal 6.8 times 10 minus 4 milliamp. Now we go to question number 8. Question number 8. So question number 8, this switch has been closed since the start of COVID-19 pandemic. So this means that it has been closed for a very long time. So we need to find the voltage across this resistor just before the switch opens and just after the switch opens. So we have to do the same process. So again, we've analyzed the circuit when the switch was closed. When the switch was closed, as you can see, when it's closed, V0 minus should be what? This is before the switch opens. When this was closed, the current here, this inductor becomes short circuit. This also short circuit, so V becomes short circuit. So V0 minus will equal 0. Now just after the switch is open, when the switch is open, what happened? When the switch is open, you can see that the voltage here, this becomes isolated. So the voltage here will be just the current times the resistor. So when we multiply 300 by 4, we will get V0 plus, which is equal 1.2 volt. Now, please pay attention now that this circuit is isolated from this one. So this voltage will stay at 1.2 volt for any time, for any values of time. So the volt at 8 microsecond will be 1.2 volt. V at 80 microsecond will equal 1.2 volt. Because this circuit, when the switching is open, this circuit becomes isolated from this circuit. Now in the second part of the question, we need to find the voltage and the energy. So the voltage V, okay, we have done with the voltage V, but now we need to find the energy stored in the inductor at different points of time. So here we need to find the energy. So in order to find the energy, of course, we need to determine the current at a different point of time. So we know that IL0 minus will equal IL0 plus. True. IL0 minus, when this was closed, of course, IL0 minus will equal 4 milliamp, and IL0 plus will equal IL0 minus. It will equal 4 milliamp. And we know from the previous circuit that tau is, we can determine tau. Then we will find that IL of t will equal 4e minus 0.11 t times 10 to the power 6. This is in milliamp. So IL0 plus IL0 plus will equal 4 milliamp. So IL at 8 microsecond, IL at 8 microsecond will equal 1.659 milliamp. IL at 80 microsecond, IL 80 microsecond, it will equal 6.029 10 or 7 amp. So from this we can determine, by the way, the expression for finding the energy, W equal half L I square, where I depends on the time. So the initial energy will equal W at 0 plus will equal 16 nanojoule. W at 8 microsecond, W at 8 microsecond, it becomes 2.752 nanojoule. W at 80 microsecond will equal 36 times 10 to the power minus 17, and as you can see the energy is decreasing as the time goes. So this is proof that the energy dissipated in the inductor will decrease with time. So we start with problem number 9. In number 9, we have this switch has been closed for a long time. Then it opens at t equals 0. So we need to find expression for IL and V. In the circuit, this expression should be valid for all t greater than or equal to 0, and also we need to find IL and V at t equal 470 microsecond. So we start as usual. So here we find the IL0 minus, of course IL0 minus, when this was closed it will equal 10 over 15. So IL0 minus IL0 minus will equal 10 over 15, which is 0.2 amp. Of course IL0 minus IL0 plus will equal IL0 minus, which is 0.2 amp. For V0 minus will equal 10 for this divider, yes. So it equal 10 over 25 plus 10 times 25. So it equal 7.143 volt. V0 plus, of course, because the voltage across the resistor can change in 0 time. The rule applies only for a current through inductor or a voltage across the capacitor. So V0 plus, because IL0 plus will be circulating in this direction, so it will be negative. So negative IL0 plus times 25. So this will equal minus 5 volt. Now our time constant tau will equal L over R. L is 40, 10 times minus 3 over R. What R? We have 3 resistors. So the 3 resistors will add up to 85. So 85, then the time constants become 0.471 millisecond or 471 microsecond. Now the expression for IL1, for IL of t will equal 0.2 E minus 2125 t. This is just 1 over tau. V of t will equal minus 5 E minus 125 t This is in amp and this is in volt. So IL at 470 microsecond, we just substitute with the T, so it will equal 0.0737 amp. And V at 470 microsecond will equal minus 1.842 volt. Now we go to question number 10. In number 10, no, number 10 is not, we will not cover number 10, so it's excluded, number 10. Number 11. So in number 11, the switch has been closed for a very long time. So now we need to find the time constant of the circuit and the voltage Vt across the capacitor at t equal tau and t equal 2 tau and t equal 5 tau. So we need to find the time constant. So of course from this circuit we need to find tau. When the switch is open, what happens? The capacitor will be connected through these three resistors. So our tau will equal R times C, of course R equivalent, so C is equal to 10 times minus 9 by 450. 450, this 100 to 300, so 450. So the time constant becomes 0.9 microsecond. Now we go to find V0 minus. V0 minus, when the switch is closed, what's happened? The capacitor becomes open circuit. So this terminal will be the same as this point. This point will be the same point because there is no voltage here, no voltage drop across here. So V0 minus will equal 4 volt. We know that the V0 plus will equal V0 minus because the voltage across the capacitor cannot change in 0 time. Now our expression for Vt will equal 4 e minus t over tau. Tau is already given 0.9 microsecond. Here we can just straightforward V at tau equal minus 1 because tau over tau equal 1, so will equal 1.472 volt. V at 2 tau equal 4, so it's equal 0.541 volt. V at 5 tau will equal 4 e minus 5, so 0.027 volt. So we move to question number 12. In question number 12, the switch has been closed for a very long time. So we need to find the time constant of the circuit, and we need to find expression for V of t, which is valid for all t. And also we need to find the stored energy in the capacitor at t equal 170 millisecond. So we take our circuit here, so we take the circuit here. So first of all, we need to find the equivalent resistor. Now when this becomes open, what happens? This capacitor will be connected with 20k, 3k, 10k, and 5k and 1k in parallel. So the equivalent resistor will be 33. It will be 33 5 over 6. It will be 33 5 over 6. 10 plus 20 to give you 30. Then 33. This one is 5 over 6. 5 over 6. So the total resistor R equivalent will equal 33 5 over 6 kilo ohm. So tau will equal 33.5 over 6k times 5. So of course times 5, 10 to the power minus 6. So the time constant becomes 169.17 millisecond. Now V0 minus, as you can see, V0 minus, we cannot use it for the expression of Vt because the voltage across this resistor. But here we should use the V0 plus, you use the voltage across this capacitor. So when the capacitor was charged, so the switch was closed here, so no current here, so the voltage on this capacitor is 12 volt. So this voltage is, we call it V1, so VC is, or VC, so V1 or VC, it will equal 12. It will equal C0 plus, because the voltage across the capacitor will not change. But here what we need to do, we need to find the voltage across here. So what we do, we apply a voltage divider. So we combine this together as 5 over 6. So 1, 2, 3, 4. All these resistors are 33.86. So V0 plus will equal 12 volt over the total resistor. All this resistor will be 33.833, of course, times K, 1000. Then this will give you the current. When you multiply the current by the resistor, this combination, which actually is 5 over 6 times 1, because the total resistor for this together is 5 over 6k. So the V0 plus becomes 0.296 volt. Now the expression for VT, becomes V0 plus is 0.296 E minus T over tau. Tau we have already found it. Tau here, it's 169.1710 times minus 3. So at T equal 1. Actually, this time is the time constant of the circuit. So V of 16.17 millisecond will equal 0.296 E minus 1. So this will equal 0.109 volt. The energy stored in the capacitor will equal half C V squared. So at that time, so 0.5 times the capacitor, 5, 10 to minus 6. Then the voltage is 0.109. 0.109 squared. So the stored energy will equal 29.55 nanojoule. So we go to problem number 13. For number 13, we have a circuit, and we need to find the voltage at t equals 0, t 984 seconds, and at 1236 seconds. And also we need to find the energy stored in the capacitor when the time equals 100 seconds. So we will take the circuit to analyze it here. So this is our circuit. So the first thing that we need to do is to find V0 minus. So V0 minus will equal, because the switch was to the right, so V0 minus will equal 20 it equal 20. So V0 minus will equal 20 volt, and we know that V0 minus will equal V0 plus, because the capacitor was charged to reach to the source voltage, because when this is connected, no current becomes here. So this point is at the same voltage at this point. At this point. Now tau will equal RC. RC. Now when the switch goes to the right, then we have only a resistor 82K. So tau will equal 82K times 12 millifarad, which is minus 3. So tau becomes 984 seconds. So the expression for our voltage will equal V0 plus, which is 20, exponential times minus t over 984, this in voltage. So V at 984, it will equal 20 times E minus 1, so it will equal 7.358 volt. V at 1236, it will equal 20 E minus 1.256, so it equal 5696 volt. In the last thing, we need to find the last part of the question, that we need to find the energy stored at 100 seconds. We know that the formula for the energy, the formula of the energy across a capacitor, the energy stored in the capacitor, W equal half C times V squared. So we need to find V at 100. So W at 100, we need to see V at 100. So V at 100 second will equal 20 times 100 over time constant 84. So this becomes 1807 volt. So W at 100 second will equal half times 12 times 10 to minus 3 times 18.07 square, so 1.959 watt. Okay, so we skip number 14 and we start with number 15. Okay, so in this circuit we need to find IX, IL, VL just before and after the switch close. IL, and this is our circuit 15. So before the switch is open, so we can redraw our circuit. So we can redraw the circuit. So it becomes 4 volt, 10 ohm, then this 3 ohm, this becomes 5 ohm, and the current here is IX, the current here is IL, and VL is the voltage across the inductor, Of course, from this circuit we can combine 3 and 5, this together to become 4 volt, then 10 is 10 ohm, and this together becomes 1.875. Now we can find the total current. The total current I will equal 4 over 10 plus 1, so 11.875, so it equals 0.3368 amp. So IX 0 minus, we apply just the current divider. So because I in this direction, so it's opposite to IX, so we say minus 0.3368 times 5 over 8. 5 over 8. 5, this is the resistor, the current divider. So 5, this resistor, 5 plus 3 becomes 8. So becomes minus 0.105 amp. IL0 minus, it is the same direction as I. So we just say 0.3368, but we apply current divider, so the current in 5 resistor, so it equals this current times 3 over 8. Times 3 over 8, so it equals 0.1263 amp. Note that the voltage when the switch was closed will equal 0 because the inductor is a short circuit. So VL0 minus will equal 0 volt. Now after we open the switch, of course IL0 plus will not change. It will equal IL0 minus 0.263 amp. And IX0 plus, what happened? What you can see, IX0 plus, because it's open, it also will equal IL0 plus. IX0 plus will equal IL0 plus because the current in the inductor will pass through this 3 ohm resistor, so it will equal IX 0.1263 amp. Now the voltage here, the voltage VL0 plus, VL0 plus is actually the voltage across the 5 and across the 3 ohm resistor. So this voltage will equal 3 plus 5, 8. So 8 times IL0 plus, so it will equal 1.0104 volt. We move to question number 16. In question number 16, we need to find I1 and IL for all t. IL and I1 of t and IL of t. So please note, in this case, always you need to redraw the circuit before the switch is open. Okay, before the switch is open. So here we can redraw the circuit. So this becomes the 8 ohm resistor, and this is the current source, 5 amp. Then this is the switch. Now what you can see here, this is becomes short circuit. These two short circuits. So here we will have 3 ohm, and we have only here the 2 ohm. 2 ohm. The current here is IL. The current here is I1. But remember, this is t is less than 0. So we can find I1 0 minus. We just use current divider. So 5 times 1.6. 1.6 is actually the combination of 2 and 8 over 3 plus 1.6, so it will equal 1.304 amp. IL0 plus will equal the same current divider, but now 5 times what? 5 times the combination of 3 and 8. This is the resistor. We combine them together, they become 2.188. So 2.1818 over 2 plus 2.1818. So the current here becomes 608 amp. So IL0 plus, of course, this is IL0 minus by IL0 plus will equal IL0 minus. So it will equal 2.608 amp. I10 plus, what when I10 plus? Now when this switch is open, what happened? What you can see that there is no current here. Then I10 plus will equal I10 plus will equal minus IL0 plus. So it will equal minus 2.608. amp. Okay, now we find tau. Tau is actually equal L equivalent over R. Tau will equal L equivalent over R. L equivalent is just 3 millihenry plus 1 Henry, 3 Henry plus 1 Henry in parallel with the 2 Henry. So it becomes 2 over 3 plus 2 over 3 plus 3 over the resistor. What actually our resistor here? 2 and 3. So over 2 and 3. So this becomes 11 over 15. So the expression for I, L and I1, so IL of t will equal 2.608 E minus 15 t over 11 amp, and I1 of t will equal minus 0.608 E minus 15 t over 11 amp. So this number 16, we skip number 17 and we go to question number 18. In question number 18, we need to find VC and VO of t at t equals 0 minus 0 plus 10 millisecond and 12 millisecond. So here we say that V0 minus when this was closed, V0 minus will be a voltage divider between this one. The one voltage will be divided onto these two resistors. So one resistor, two resistors. So we just do a voltage divider. So V0 minus which is VO0 minus VO 0 minus 1 over 5 1 over 2 plus 5k times 2k. So it's equal to over 7 voltage. VC0 minus will equal 1 volt here. This is 1 volt, but it divides on the combination 4 and 2 become in series. Then together they become in series with 6. So 6 and 2, 6 and 6. So this together becomes 3k. They become 3k. So the voltage here 1 volt and 1k, and here we have 3k. So it equal 1 over 1 plus 3k times 3k, because the voltage is here, so it becomes 3 over 4 voltage. Now we know that VC0 plus will equal VC0 minus, which is equal 3 over 4 volt. VO0 plus will change, yes, because this source is no longer here. So we will find the voltage divider again. The voltage VC here is the same voltage as the voltage here. So this voltage will be divided over 1, 5, and 2. So it will equal VC 0 plus over 1k plus 5k plus 2k times what? Times 2k. 2k, so it will equal 3 over 16 volt. Now we find the time constant. So the time constant will equal R equivalent times C. R equivalent is just this resistor together become in series. So 1, 5, 2, so it becomes 8. Then 8 in parallel with the 6k. Then the 6 this resistor in parallel with the 6k, and also in parallel with this 6k. So it becomes 3K in parallel with 8K. 3K in parallel with 8K. So the time constant becomes the time constant become 24 over 11 millisecond. 24 over 11 millisecond. So here we can find the substitution for V1 of Vc of t and V of t. Vc of t, V0 plus is equal 3 over 4. So it's equal 0.75 e minus 11 over 24t times 10 to the power 3 volt. Vo of t will equal 3 over 16. 3 over 16, the exponential is t over 24 times 10 to the power 3 volt. Then Vc at 10 millisecond will equal 0.0077 volt. Vc at 12 millisecond, Vc at 12 millisecond will equal 0.0031 volt. Vo at 10 millisecond will equal 0.019 volt. Vc at Vo at 12 millisecond will equal 7.63 10 times minus 4 volt.